Okay, so today we are going to talk about bagging and boosting. Bagging and boosting are basically two different methods that combines multiple machine learning models into a single one. If we are talking about the bagging methods, in bagging methods, we instead of creating a one long model or one large model, we split our data set in training data set into multiple subsets, and we train multiple models and we combine them based on average or based on majority weight. If we're talking about regression, we go with average, and if we're talking about classification, we go with majority vote. And if we are talking about the boosting, in boosting, we train a model and we try to improve it as much as possible. And this helps us to get a perfect model for our data set. Now, these are two different approaches that basically overcome or overpower the single model approach that we are doing till now, like decision tree, logistic regression, and all that. No, there is a thing called overfitting, right? Now, if do you have any idea about overfitting and underfitting? Okay, so let me explain it. This is our data points, right? And we have to create a model that train on these data points and that predicts that how this line will go, right? Now, let's talk about the simplest model, linear regression model, and we say this is something like this, right? Now, this will be a kind of perfect model that these points follow along and it will go along, right? Instead of doing that, I just don't want to mess with beta naught, beta one, and all that. I just create a line here and I say, yeah, this is some kind of pattern that we are seeing here. This is the simplest model, right? This is what we call underfitting. It means that we didn't even bother about catching the data, right? That's what underfitting is. Now, instead of doing that, if someone say, we know these are the points, instead of doing a straight line, what we do is we create a line that combine all the points, right? Now, on theory, this line is perfect. It's going to meet all the points, right? But it have no intuition about where the data is going. It's going sometime upward, sometime downward. Now, when we do prediction based on that, it will be the worst predictions, right? So that's what we call overfitting. Now here we fit the training data so much that we don't even have any idea what testing data will look like. So this was overfitting, and if you're talking about the underfitting, we will draw a line somewhere here or somewhere here that doesn't even bother about the points. When we use multiple models, we basically reduce the overfitting. Okay, because if we are trying to create a one good model, we will train it a lot. Like for example, if we're trying to create a decision tree, we want good results, we are going with 10 or 15 layers of tree. This is going to be one complex tree, right? Instead of doing that, if we take 10 different trees on smaller sets, that will be much simpler approach. It obviously improves the accuracy because instead of one model, we are using 10 different models or 8 different models. So that helps us to do that. Now, it is also less sensitive to the outliers. Now, we know that outliers are the points that are some kind of mistakes in the data set that are far away from most of the data. Now, if they influence so much in the one model, in the other models, their influence will not be as much as compared to the single one, right? So that's why when we use assembling methods, they basically overpower or overshadow the sensitive outliers. Now, here is the term bias variance trade-off. Whenever you go for a data scientist interview or any data related interview, machine learning related interview, this is a kind of question that everyone will ask. What is bias variance trade-off and what do you know about that? The bias variance trade-off basically is trying to adjust between the overfitting and underfitting. So your model is not much overfit and it's not as much as underfit. Now, if we are basically in bias variance trade-off, bias basically means error that we make in our model, right? And variance is basically the variance, the spread of the data. Now, when we say bias variance trade-off, we basically means we have to make a trade-off that how much error we can accept and how much variance it should have. Like here, if we are not expecting any error, it means our variance will go boom, like we will have a lot of variance in the testing data set, right? So we need to decide between a simple model, or we don't need a very simple model, and we also don't need a very overfitted model. So that's what bias variance trade-off is. If you make a simple model, you basically increase the bias or increase the error, you reduce the variance, right? But if you are going to make a more complex model, we will decrease our bias, but variance will increase and we will overfit our model. So that's kind of problem that we have to deal with whenever we're trying to train any model. Let's talk about different models that we have in bagging and boosting. Now, in bagging, the most famous method is random forest. Now, as we know, decision tree comes from a tree-like structure, and random forest basically means a forest of trees, like we combine a lot of different decision tree models in a single model. And after that, we have three different boosting methods like AdaBoosting, gradient boosting, and XGB boosting. We will discuss them in the next few minutes. Now, when we are in Python, we use packages, right? And it is not possible that every time you're trying to use a package and it's already present in your environment. So whenever you need to install some package, you use a command pip install xpip install. Now, pip is a package manager that basically manage all the packages that are created for Python, and install is a prefix for it. So whenever we use pip install and the name of the package. Now here we are going to use XGBoost, and XGBoost does not include in Google Colab, so we have to install it first. Machine learning is heavily dependent on the sklearn or scikit-learn package. Okay, so even when we go to the deep learning, the next step of machine learning, deep learning basically that helped us to create ChatGPT and all kind of language models. In the deep learning, we will also see that sklearn is heavily used. We are importing packages in sklearn. We are importing packages related to data split, cross validation, and grid search. Scalar label encoder we discussed in the data cleaning session. Accuracy classification we discussed in the logistic regression session. Mean square error, R square error we discussed in linear regression session. So basically, everything that we are using here remain the same with almost all the models. Like if you're talking about classification models, we go with this class like accuracy, classification report, confusion matrix. If you're talking about regression model, we go with R square and mean square error. Okay, and this is kind of common step between any kind of model. So we have to split the data and we have to go with cross validation and all that. Here we have decision tree classifier, we have decision tree regressor, and here we are also going to use these packages. From sklearn ensemble, we are going to import random forest classifier and AdaBoosting regressor, AdaBoosting classifier, gradient boosting classifier, gradient boosting regressor, and different bagging classifiers and voting classifiers and regressors. So basically, there are different models that belong to these techniques. Okay, now I added a check here, like if you were unable to install the XGBoost package, so you will get an error that you need to install the XGBoost package. Other than that, this code doesn't have any functionality. Like if you import a package and if it works fine, it will print just XGBoost available. If it doesn't work, it will show that we need to install the XGBoost, and we can install it with the pip install XGBoost. For the data set, we are going with, again, the wine data set, and we are not importing it from the CSV file. We are just importing it directly from the sklearn package. These are some styling parameters, and let's now go to the, now we load the data set, we saved it, we have the independent variables, we have dependent variables. Again, this is going to be the same stuff here. We use training test split. Here we're using 70% data for training and 30% data for testing. Again, we want to stratify, that's why we just said that we are going to stratify based on our dependent variable. Now what we're going to do here is we are going to run some solo models like decision tree, and then we will run some big models like random forest and boosting models, and then we will see that how much boost we get in the accuracy and the stuff. If we take a look at the code, we will see that most of the code is similar. When we are talking about decision tree classifier, we go with the decision tree classifier function, but if we are going to use random forest, the boosting model that basically combines different trees into a single one, we go with the random forest classifier. Also, if you want to explore something about any kind of function, you can just place the cursor on it and it will open a documentation for that. Right now, the rest of the code is going to be the same. We will give it training data, we will give it training data for X column or independent columns and training data for dependent column. And based on that, we generate predictions like we do in all kind of models. And once we have the predictions, we give accuracy scores, the predictions and the actual data, and based on that, it will give us the accuracy. Now, in that case, we are getting accuracy of 0.96 from decision tree, basically 96% accurate. And but random forest is giving us 100% accuracy. Okay. Now, since it's a dummy data set, it's a very small data set and it's designed for studying. That's why we're getting such a big numbers. But when we are working on real world data set, we don't see that kind of 100% prediction, the 96% prediction. We mostly revolve around 85. At the higher end, we go to the 90, 91. Now, the random forest classifier, decision tree classifier, they all have predefined feature importance. Okay. So whenever you train a model, here we train dt dot classifier, rf dot classifier, we can just write dot feature importance and we will see the feature importance of all the columns. And now we will have a feature importance related to all the columns. So that's why we also need to add the names of the features so we can create a proper data set here. Okay, with the pd data frame. Again, we sorted the values to get a clean plot. And now here we are talking about the top 10 features. That's why we are using feature importance dot head. Dot head basically gives us the top rows. And if you're specifying 10, it means we need 10 rows from the top. Okay. X is going to be the importance and Y is going to be the feature. Now, importance is basically the feature importance that we generated from the classifier, and feature is basically the name that we extracted from the data. The rest is just label and title and all that. Now, another thing that we need to understand is when we talk about random forest, we also need to specify that how many trees we want. Okay. For example, here we implemented random forest classifier and we also give it that we need 100 trees. Okay. Now, if your data set is small, like for example, if your data set has only 1,000 rows, okay, and we are trying to create 100 different trees from it, so it will not make sense. So we need to reduce the number of trees. Okay, so we will always need to adjust that parameter, and we can also adjust the parameters based on the grid search that we did in decision tree. We will do it here today as well. Okay, now we can check that how accuracy works with the different number of trees. We can give it a range of different number of trees like 1, 5, 10, 25, 50, 100, 200, 500, right? Sorry, did you say something? Can you hear me?
No, no, nothing. No. Yes.
Okay. So now what we did here is we just created a for loop that go through this range and it will just train the models for 1, for 5 number of trees, for 10 number of trees. Okay. And once it do that, we also try to plot it to see that how increasing the tree works on our end. Okay. Now, if we take a look at the plot, our data set was small and we can here we only take one tree. Here we take 100 trees. Now, if we take 100 trees, we are getting 100% accuracy. Now, If we're doing 200, 300, 400, 500, this is all complexity that we are adding to the model. So this is not going to help our model, right? So that's what we need to avoid whenever we're trying to train a model. It doesn't make any sense, like if we can train it for 1,000 times, so we should train it for 1,000 times. Okay, so we just need to find the optimum number where we get the best accuracy. In that particular case, it will be something around 30 to 35. After that was meaningless and we don't need to do that. Now for the boosting, we train single model, and we after that we try to make it better, right? If we're talking about AdaBoosting or adaptive boosting, we adjust the weight of the misclassified instances. Like we trained a model and we are getting some misclassification. So what parameters or what hyperparameters we have, we will adjust them to improve our misclassifications. In gradient boosting, we try to improve our accuracy based on gradient descent, the formula that we used in linear regression and logistic regression to get beta naught and beta 1, right? Now, XGBoost basically also add a term of error that helps us in that we also call regularization. It's basically extension to linear regression where we have two different kind of L1 and L2 regularization, but that was not part of this course, so we didn't include it till now. Basically, it's gradient descent with an extra term of error. Okay, so basically different. So we have a gradient descent formula and we add another term and it will be another formula that will be little bit better than gradient boosting. Again, if we need to train it, we will have these models in the sklearn package. We need to give number of estimators, learning rate, random state, and max depth. Okay. And now since we are creating 100 different trees, if we are it will all whenever we are trying to do with multiple trees like random forest or ADA boosting and all these models basically revolve around the same tree, but implementing more than one time. Okay. So we need our main model, the same tree here should be weak. Okay. We don't want to create a complex model 100 times. So we go with the weakest model. That's why in this case, we are trying to say that max depth is equal to 1. And it's not specific to this one. If we are going with random forest, we can also do that. And in the same manner, we can do this with the XGBoost and gradient boosting. Again, these are the hyperparameters that we can adjust to increase or decrease the accuracy of our model. And we can do that with the grid search. Now, if we run a classifier with the ADA boosting, and then we will just run a simple decision tree, and we can compare it that ADA boosting accuracy is 98%, but a simple tree is only 61%. Okay, so that's basically the benefit that we achieve from overtraining our model, or our training again training our model more than one time to improve our weights. Again, we did the same thing just with the learning rate. So how the learning rate works. Again, higher number doesn't mean we are going to get a better model. We just need to find the optimum number where our model perform best. Okay. Now in that particular case, our model perform best around 1. Now, y-axis basically represent test accuracy. We train a model on training set. We then test our model on the testing set, and based on that, we get the accuracy. Like in that particular case, we are getting something like 98% accuracy. It means if we take 100 predictions from our model, 98 are going to be correct based on the testing data. Now, if we take a look at the rest of them, they are going to be the simple. We just need to specify the depth, learning rate, and all that. Okay. Also, another thing that we should discuss is feature importance. If we are talking about, for example, we're trying to train a model, like we downloaded a data set and it contains a lot of information, like we have 10,000 or 100 different variables. Okay. One is dependent variable, and we include 99 variables into independent. Okay. Now, but the problem is to tackle this problem, we need to clean 99 different columns, and we also need to make sure everything is in good quality, we have a good quality data set for all the independent variables. And when we go through all of that, at the end of the day, we realize that only there were 10 or 20 variables that were significant and that were important and that we should have included. Now, rest of the variables and rest of the work that we did was just for something that we don't need to do, right? So that's why we need to understand the feature importance. When we train a model is giving us accuracy. Now, if we are tracking about this data, we have 96% accuracy. That's such a good number, right? And if we add more columns into it, like we are trying to train a model on 10 columns, and we are trying to add 20 more columns. Now, 10 columns are already achieving 96% accuracy. If the other 20 columns are not relevant, we are going to see reduction in our accuracy. So it doesn't mean if we are trying to add more columns, our model will get better. In the same manner, a higher number in hyperparameter basically doesn't represent that our model is going to be better. So these are some small things that we should be careful about. Now let's talk about these plots. We train our model gradient boosting. Based on that, we get the accuracy score. We created the model, we get the feature selection. After doing that, we are trying to create the plot. Now, what we are trying to do here is we are trying to create the plot based on testing and training accuracy. Now, if we look at the training loss, now when we increase the number of iteration till 20, we see a significant jump that we are reducing the error. Till 40, we are reducing the error, but after that, we are not reducing any kind of error. So after what we do here is basically waste, right? Now, if we look at the accuracy here, now if we look at the accuracy here, we are increasing the iterations, right? Based on the test set. Now we are talking about the test set. We get the highest accuracy around 38, 37, but after that we see a reduction in the accuracy. Why we see the reduction in the accuracy? Because we are overfitting our model. Now, if we increase it more, we will see the more loss or more reduction in the test accuracy. So that's how basically machine learning works. No matter what model we are working with, we need to make sure we train our model and we train our model significant enough. We don't overtrain it. If we are overtraining it, well, basically means we are going to suffer with the bias variance trade-off. Now here we did a little bit of comparison between different models. Like if we implement all these model on the same data set, then how much difference we are going to get. Okay. And here we are getting with the decision tree, we have 86% of the accuracy. Random forest gives us 96% of the accuracy, and 94%, 88%, and 95% of the accuracy. Now here we are talking about the cross-validation mean accuracy, right? Basically, we discussed cross-validation in the last session, like where we create, instead of one training and testing set, we create 5 different training set and total divide the data into 5 different sets. We take 4 as a training, 1 as a testing, and we keep shuffling them to get our accuracy. And this is a mean accuracy. So basically, we take the average of all models that we got. Do you have any question? Okay. Now we can also visualize these models with box plots, with bar charts, and all that. Okay. Now this is another example. Here we are dealing with the regression problem. And when we are dealing with the regression problem, instead of confusion matrix and accuracy, we are going to discuss mean square error and R square value. And now here we are going with linear regression, decision tree, random forest, AdaBoosting, and gradient boosting. Now here we are getting highest R square value with the linear regression model. But it doesn't mean that linear regression model is better than all these. Just in this particular case, our data set is more suitable for linear regression. Or we can say our data set was linear. Like all these models basically reveal the non-linear patterns as well. Since our data set was linear, that's why we're getting better accuracy with the linear regression model. Okay. But in the real world scenario, when we're working on some kind of problem, we see that we random forest and XGBoost and these boosting models basically perform very well. as compared to the single-sided models like logistic regression or linear regression or decision tree. Now let's talk about the hyperparameter tuning. Now, when we were talking about the decision tree, we talked about three hyperparameters: max depth, minimum sample split, and minimum sample leaf. Okay. And here we have another parameter, number of estimators, that basically represent number of trees or number of models that we are going to train. Okay. The rest of the code is going to be the same. We just created a dictionary and we provide this dictionary to the grid search CV. Now, grid search CV, we will provide it with the model that we are going to use and this dictionary. Now, based on that, it will train all the different combinations of models and it will return us the best model that we can get. In that particular case, we are getting max depth is equal to 3, minimum sample leaf is equal to 1, minimum sample split is equal to 2, and number of estimator is equal to 200. Now, that was all for today. We have some notes here that you can also go through.